Welcome back to Valiant PE. Today's topic, bolted joint slip capacity. Let's go. Okay, we have a tough example problem today. What is slip capacity? We're going to figure it out. So as usual, we're going to solve the problem and then go through what makes it a PE level problem. And as usual, every time we start a question, do something to reset yourself mentally. Take a breath. Do something. I like to breathe deep, breathe the question slowly, and then write immediately what I'm solving for. So here we go. 3 steel plates, each with thickness of 10 millimeters, are bolted together in the permanent configuration shown. What is the slip capacity of the joint? Okay, looking at my answer choices, I know immediately I'm solving for a force with a value of newtons, or units of newtons. Then I'm going to look at my imagery. Do I have any info in the imagery not given in the problem statement? I do. I've got a bolt grade. These are M20 size, grade 10.9. I've got 3 of them. And I've got a mu value for steel-on-steel friction surfaces. Okay, good. Let's solve. What is my slip capacity equation? That's mu times my preload force times number of bolts times number of friction surfaces. To solve this, what is my preload force? Well, preload force is my proof strength times my tensile stress area. But this is a permanent joint. So that is a clue that tells us we're going to derate our proof load, which is this, by down to 90%. Okay, let's put some values to it. 0.9 times 830 megapascals times 245 millimeters squared. Let's convert our units. I'm just going to rewrite this. I am slow and I like to write everything all the way out. Just make sure I don't miss any units. I'm going to convert millimeters squared to meters squared here. Yikes, that was terrible. 1 million millimeters squared. Okay, millimeters cancel, meters cancel. I'm left with newtons. Let's solve for it. My preload force is 183,015 newtons. Now, critical here, this is per bolt. So now let's just go solve our slip capacity equation. RS is equal to mu, which is 0.19 times my preload force of 1 bolt times my number of bolts times my number of friction surfaces. What is my slip capacity? 208,637 newtons. Okay, do I have that anywhere up here? I do. Answer D. Okay, great. Let's talk about it. This is a pretty simple algebra problem. Not a whole lot here. 2, maybe 3 steps. But what makes it tough? Because the phrase slip capacity doesn't appear in any machine design textbooks. So let's go. First thing that we're going to need to know, just make some assumptions right off the bat. We're going to use coarse thread bolts here, not fine thread. With bolts, I would expect a call out if it's going to be fine thread, so let's just go with coarse. I think that's a reasonable thing to start with. Okay, things that you need to know. The key to this problem is knowing all the building blocks and how to put them together to solve a tough example. The building blocks are simple. Slip capacity, what does that phrase mean? That's not in Shigley, it's not in MERM, it's not in the reference manual. All it means is resistance to slipping. And how do you find how much external load a shear joint can handle if we're relying on bolt preload? Okay, my resistance to slipping is simply my preload force times my friction coefficient. Preload force times friction coefficient. It goes one step farther than that though, and I'll show you with an example. Up in the top right up here, this is a side view of our joint. So let's draw a free body diagram of what the middle plate, what forces are acting on the middle plate. First thing is we've got 3 bolts acting in compression. We've got a force pulling to the left. Pretty simple. Where's our friction force? We've got a friction force acting here and here. Okay, so our slip capacity is, well, it's a friction problem. How do we find friction? You take You take mu times your normal force. What's your normal force in this case? It's all of your preloads. What's your mu? It's given, so you can solve for that. Now notice there are two slip planes, so this is where the M value comes in. Two slip planes, double the friction force. So N is preload. How many preloads do I have? I have 3. 1, 2, 3. So slip capacity is a friction calculation for the total number of bolts and the total number of slip surfaces. That's all it is. That's simple. In statics, you learn how to do friction problems. Mu n, that's in statics, okay? So let's not be intimidated by the phrase slip capacity, and it really would throw you for a loop if you've never seen it before, and you probably haven't. So the next item that makes this critical, and we've already talked about it, is two slip planes, doubles your friction force. If you just used one friction force here, not enough. You're going to get the problem wrong. You get the value of, it's going to be half. So now we've covered slip capacity, let's talk about bolts just a little bit more deeply. So when we're dealing with bolts, what is our yield criteria? If we're using torque to yield fasteners, it's yield stress, but that almost never happens and probably you won't see that on an exam. We're going to use proof strength, not yield or tensile strength. When dealing with bolts, our failure criteria needs to be proof strength. The next thing is, how do I find my preload force? It's not stated. Well, you need to know that preload is a function of tensile stress area, not nominal diameter of the bolt. Tensile stress area, not nominal diameter of the bolt. Okay, so preload force is equal to proof strength, that's an S, wow, that's a bad S, proof strength times your tensile stress area. That is given in the reference manual. And lastly, for permanent joints versus a non-permanent joint, we use 90% of our proof load. Permanent. Okay, so this is given in the manual. There's a difference between permanent and non-permanent joints, and you choose your preload value based on a derating of your proof load. So all of these things are simply stated in a machine design textbook. Shigley's a great example. So if you know all of these, well, this guy isn't, but all of this is. If you know these building blocks, you understand preload, tensile stress area, permanent joints, you can solve this problem. I think that's the key to all PE example problems, is know the building blocks, then you can start putting them together to solve a tough problem. But the building blocks are easy, but the only way you're going to know them is if you go and read about them and learn them. Lastly, on the example itself, a couple things here. You're going to have to do two lookups to solve this problem. Tensile stress area is given. There's both fine and coarse thread, so you got to know A, where they are, B, what series you're using, and C, is it coarse or fine. And then lastly, you need to look up what grade 10.9 proof strength is. Again, charts in the back, so go look for it. And if that were not enough, to add insult to injury, the answer choices are tricky, all of them, okay? If you only used one shear plane, you would have gotten answer A, half the slip capacity. If you had used 100% of your proof load and did not derate to 90 or 75%, you would have gotten this guy wrong. And then lastly, answer C, if you had used yield strength, 940 megapascals instead of proof strength, which is 830, you would have got it wrong. So, guys, this is a simple problem. The building blocks that are underneath it are simple, but you gotta have done the work to go read the books and done the practice of the reference manual to know where these things are, and you can get it. So remember, you don't have to be a genius to pass this exam. See you next time.